Hello, and welcome to the lecture on 4.5. Today we're going to talk about exponential and logarithmic equations. Let's start with exponential equations. This section is actually a very good section. We're going to talk a lot about how to solve for x when we have an exponential in our equation. Let's start with if we have something like this. A to the x is equal to a to the y. Since we have the same base, these exponents should also be equal. Now there's a reason for this. It's not always the case in other types of functions, but in this type of function, 100%. This is always the case where x and y will be equal if you have the same base. So this will imply that x is equal to y. Let's do an example of some stuff like this. Suppose we have something that looks like this. 3 to the x is equal to 81. Well, it doesn't look like they have the same base at face value. But if we convert 81 into 3 to the 4th power, then we actually have the same base. So this is the same thing as 3 to the x is equal to 3 to the 4th, which then means that their exponents are equal because we have the same base, which is 3. So this then means that x is equal to 4. Now let's do one that's a little bit more challenging in a couple of respects. Suppose that we have 2 to the x plus 1 is equal to 4 to the x minus 2. How do we do this one? First of all, note that we have an x value in each exponent, but also note we have different bases. So how do we actually solve this problem? It's actually not as hard as you think. So first, remember 4 is a power of 2. So we can rewrite 4 as 2 squared. So this is the same thing as 2 squared to the x minus 2 power. Now, because we have something with an exponent to another exponent, we multiply the exponents. So we'll end up with 2 to the x plus 1 is equal to 2 to the 2x minus 4. Don't forget to distribute this 2 when you multiply it. So 2x minus 4, because it distributes to both of these terms. So now we can set their exponents equally to each other because we have the same base. So we have x plus 1 is equal to 2x minus 4. We simplify by subtracting an x and adding 4. So we end up with x is equal to 5. Now we can check to make sure that our answer is correct. It will be correct, but I want to check anyway, just for practice. If we take our 5, plug it in for x, we get 2 to the 6th power. If we take our 5, we plug it in for x, we get 4 to the 3rd power. 4 to the 3rd power is 64. 2 to the 6th power is also 64. Now there's other types of problems where we might want to solve using a calculator. Let's do an example of this. Suppose that we have 3 to the 2x is equal to 5. Now these bases don't really have a relationship with each other. What I mean by that is that 5 is not a power of 3 and 3 is not a power of 5. So how do we solve this? Well, we just end up taking the logarithm of both sides in this case. If we wanted to use a calculator at the end of this problem, you'll want to choose either ln or log. Now, if you remember, log of something is equal to log base 10, but this button, log, is on your calculator, so you can actually use it. I'm going to use ln just because I think ln is more important and is more commonly used in later versions of mathematics like calculus. So if we take the ln of both sides, we get ln of 3 to the 2x equals ln of 5. Now, there's some reasons that we can do this that you don't need to know for this class, but just suffice it to say that you can take the log of both sides, and it is still an equivalent equation. This 2x can come down to the front. So we have 2x times ln of 3 is equal to ln of 5. Then we can divide by 2 ln 3 to isolate our x. We end up with x is equal to ln of 5 divided by 2 ln of 3. And that's our solution. Now, because ln is on your calculator, you can actually solve this in your calculator. But I'm not going to do that. Try one. Solve the equation. E to the 2x plus 1 equals 16. This will be very similar to the previous problem. Okay, I'm going to do a couple more examples because these next examples are sort of a combination of this chapter and previous chapters that we've learned. Suppose that we now have quadratic equations involving exponentials. Let's do an example of this. Now, these ones are a bit tricky, but suppose we have e to the 2x minus 3e to the x minus 10 is equal to 0. How do we solve an equation like this? Well, it's a little bit tricky because it's not in a form that we generally see. It's not in a form that we've seen before. So this is a new style of problem. As I said, it's a mix of chapter 4 and chapter 2, chapter 3, where we work with polynomials and factoring. But notice that this is actually a quadratic form. So what we can do is say, let w equal e to the x. Now this then means that w squared is equal to e to the x squared, which is the same thing as e to the 2x. Notice that we have an e to the 2x in our problem, and we have an e to the x in our problem. So this will become w squared minus 3w minus 10 is equal to 0. Now this we can do. We've done these before. All we need to do is factor, and then we use the zero product property in order to solve the equation. So here we're multiplying to negative 10 and adding to negative 3. Two numbers that multiply to negative 10 and add to negative 3 will be negative 5 and 2. So we factor this down to w minus 5 times w plus 2 is equal to 0. Then we use the zero product property. If we have a product of two terms that's equal to 0, then one of them, at least one of them, has to be 0. So we can actually look for the w values that will make this equation, this product, 0. So we go w minus 5, and we look for when this is equal to 0, because if this is 0, then this product is 0. And we look for when w plus 2 is equal to 0, because again, if this is 0, then this product will be 0. So we end up with w equals 5 and w equals negative 2. Now, are we done here? No, we're not done yet. The reason we're not done is because we've solved for w. Our original equation is in terms of x. We're looking to solve for x, but we haven't done that yet. We've only solved for w. So we take our w, and we resubstitute. E to the x is equal to 5, and e to the x is equal to negative 2. Then all we need to do is take the ln of both sides, or convert this into its logarithmic form, and we end up with x is equal to ln of 5, and x is equal to ln of negative 2. And is this it? Again, no. We need to check our answers to make sure that, first of all, they're within the domain, and we can also check them within this, within the original equation. Negative 2 is not in the domain of a logarithm. Remember, the domains of logarithms are from 0 to infinity. Basically, you can only plug in positive numbers as an input to a logarithm. Negative 2 is very clearly not positive. So this cannot be used as an input for a logarithm, which means we exclude this. It's an extraneous solution. So our only solution is x is equal to ln of 5. Now we can check this. E to the 2 ln 5 minus 3e to the ln 5 minus 10 is equal to 0. Is this a true equation? Well, first, this 2 will need to move up to be a power on the 5 because this 2 is sitting in front of a logarithm, which means we can move it to be a power of 5 as the input for our logarithm. So we end up with e to the ln of 5 squared minus 3e to the ln of 5 minus 10. And we're still checking to see if this is 0. Now, e to the ln of something is that something. This right here, e to the ln, this is composing a function with its inverse. And if you remember, f of f inverse of x is equal to x. And f inverse of f of x is equal to x. This composition is from chapter 2, I believe. Now that's exactly what we're doing here. E and ln are inverse functions of each other, so when we compose them, we get x, which means e to the ln of 25 is 25. 5 squared, of course, being 25. Minus e to the ln of 5 is 5, so we have 3 times 5 minus 10. And you can see 25 minus 15 minus 10 is actually equal to 0. So this is a solution. Let's do another example like this. Suppose now we have the equation 2x e to the x plus x squared e to the x is equal to 0. Now this one might be a little bit trickier for one particular reason. Once you understand that reason, then it becomes a little bit easier, I think. Let's start by factoring out what we can. We can factor out an e to the x. We also have an x that's common in both terms. So we have x e to the x 2 plus x is equal to 0. Now, if you notice, we have x times e to the x times 2 plus x. So we actually have a product is equal to 0. It's a product of 3 different things is equal to 0. So now what we do is we set each one of them equal to 0 because of the 0 product property. If we have a product that is equal to 0, then at least one of these things has to be 0. So we look for when each one is equal to 0 so that we have our solutions. So we have x is equal to 0, e to the x is equal to 0, and 2 plus x is equal to 0. And we determine when each one of them is 0, because if this is 0, then this is 0, which means that this entire product is 0. If e to the x is 0, then this e to the x is 0, and we'd have something times 0 times something, which is 0. Same idea with x being 0. Now, here's the part that gets a little bit tricky. If you haven't studied exponentials for very long, sometimes this is a bit confusing. E to the x is actually never equal to 0. E to the x, remember, is always positive. If you recall what the graph looks like, it looks like this. Notice that we actually never touch the x-axis, i.e. when y is equal to 0. This means that this graph is actually never equal to 0, which means e to the x is never actually equal to 0. So we could just ignore this part. You can actually divide out that e to the x, but I don't recommend doing that just for consistency with other types of functions. Many times students get confused and they start dividing out some of the solutions that you might get. So we end up with x is equal to 0 and x is equal to -2 as our solutions. The e to the x doesn't actually really play a role in this type of equation when you factor it out. It's just sort of there to confuse you a bit, but these types of problems do actually exist. The next section that I want to talk about is going to be logarithmic equations. Basically the same exact thing that we just covered, but instead we're going to be talking about logs instead of exponentials. I'm going to give you a guideline on how to solve these types of equations. 1. Isolate the logarithmic terms on one side of the equation and combine the log terms. 2. Write the equation in its exponential form. 3. Solve for the variable. 4. Check your solution set with the original equation. Let's do a simple example here. Solve the equation. Log base 3 of x plus 2 is equal to 2. All right, so note here that we have the logarithmic term isolated on its side of the equation. There are no other logarithmic terms to combine this with. So now we want to write it in its exponential form. Now, remember, when we have a logarithm like this, this is true if and only if 3 to the second power is equal to this expression here. That's the input of the logarithm. So here we have 3 squared is equal to x plus 2. And then we solve for x. So we get 9 is equal to x plus 2, which means x is equal to 7. So we've isolated the variable now. So our solution is x equals 7. We now just need to check it with the original equation. Plug in 7 here. 7 plus 2 is 9. 3 squared is equal to 9. So this is a true solution. Let's do another example. This one, where we're going to have to combine some logarithms. So we have to work a little bit more on step 1. Combining logs. Log base 9 of x minus 5 plus log base 9 of x plus 3 is equal to 1. So notice here, we now have two different logarithmic terms, and it's equal to 1. Now again, they're isolated on one side. We just need to combine these two. We already have the same base, and we have a sum in between, which means we multiply their respective inputs. Now we have log base 9 of x minus 5 times x plus 3, like this, and it's equal to 1. Now we change it to its exponential form, so 9 to the first power is going to equal x minus 5 times x plus 3. 9 to the first is equal to x minus 5 times x plus 3. We FOIL this out because we need to get this equal to 0 somehow. So I need to subtract the 9 over, which means I need to FOIL this out in order to be able to combine like terms and then refactor. So right now, let's FOIL it out. We get x squared minus 2x minus 15 is equal to 9. If I subtract the 9 over, I get 0 is equal to x squared minus 2x minus 24. Now we need to refactor. So here, we're looking for two numbers that multiply to negative 24 and add to negative 2. Those two numbers are going to be x minus 6, x plus 4. So we get x is equal to 6 and x is equal to negative 4. Now we just need to check both of these solutions in our original equation. We have our solutions, or the solution set so far, but we need to check to make sure that they are true solutions. Remember, logarithms can only take positive values as an input. That's going to be where some of these solutions fail sometimes. For instance, in this case, x is equal to negative 4. If I plug that in here, I get a negative 4 minus 5 is a negative 9. Log base 9 of negative 9 does not exist. So x equals negative 4 is actually not a solution. It's extraneous. However, if we plug in 6, we get 6 minus 1 and 6 plus 3. And then it's log base 9 of 1 plus log base 9 of 9, and that's going to equal 1 for sure. You can check if you need to. Try one now. Log base 2 of x plus log base 2 of x minus 3 is equal to 2. This is actually just like the previous problem, so if you follow those steps, you should be able to get it relatively easily. All right, the next topic I want to cover is compound interest. Recall, A of t is equal to p times 1 plus r divided by n to the nt. This is compounding interest n times per year. A of t is equal to p e to the rt. This is compounding interest continuously. And we're going to use these equations to solve some of these problems. Specifically, now we're going to be looking for t because it's in an exponential. If an investment has an annual interest rate of 6% compounded monthly, how long will it take for the principal to double? So we're compounding monthly means that we're using this top equation because we're compounding 12 times per year, not continuously, which means we have the equation A of t is equal to p 1 plus r divided by n to the nt power. Now again, n is going to equal 12 because we're compounding 12 times per year, which is monthly. R is equal to 0.06, that's 6%. And that's all we know. So we need to understand what we're looking for, and we also need to understand how to be able to solve this type of problem with the information given, because these types of problems feel like they don't give you enough information, but they do. What are we looking for? We're looking for how long it will take for the principal to double. How long? That should spark something in your mind. When we're looking for something that says how long, what variable are we looking for as an answer? T. We're looking for how long means we're looking for a length of time. And t is that length of time. So this is what we're looking for, t. Now, what is the principal? We don't actually know the principal. So how do we solve this type of problem? Well, we don't really need to know the principal because we're looking for the length of time that it'll take for the principal to double. So we know after a certain period of time, our A of t will actually be twice the principal. So let's just leave the principal as p for now. Now, what we want to do is say, well, our A of t is going to eventually be twice the principal, will equal our principal times 1 plus our rate, 0.06, divided by n, which is 12, to the 12t. Now we have everything that we need. We can just divide out the p. Divide both sides by p, and our p will go away. This is why we don't actually need the principal, because we're looking for the length of time it takes for the principal to double. If we divide both sides by p, we end up with 2 is equal to 1 plus 0.005, the 12t. Now, this problem is in this section because we need to use logarithms in order to solve it. When we add these two together, we have 1.005 to the 12t. We need to be able to get this t out of the power. And in order to do that, we use logarithms. So we take the log of both sides. I'm going to take the ln of both sides. Now we have 1.005 to the 12t as an input for our logarithm, and we have ln of 2 on the other side. If you want to use log base 10, and use your calculator, that would be okay as well. But I like to use ln. It's just something that I'm used to. So we can move this 12t down to the front because it's a power on the input. ln of 2 will equal 12t times ln of 1.005. And then we just divide by 12 times ln of 1.005, and we have our solution. We have ln of 2 divided by 12 ln 1.005. If we actually use a calculator, we end up with 11.58 years. Want you to try one now? If an investment has an interest rate of 4% compounded semi-annually, which is 2 times per year, how long will it take for the principal to triple? Now this is exactly like the last problem, except instead of looking for when the principal will double, we're looking for when the principal will triple. All right, that's going to be it for today. I will see you all in the next lecture.